Okay, so this topic, we're looking at photosynthesis, which is, many people would agree, not just me saying this, it's the most important physiological process on the face of the earth, because we wouldn't be here without photosynthesis happening. We utterly depend on it. And so um, for this class, when I get into photosynthesis, there's actually like two parts of photosynthesis. There's the light reactions, like how do they capture sunlight energy and do their thing. And then there's the second part of photosynthesis is how do they take in CO2 and make sugar from that. So in this class, I tend to focus more on CO2 coming in and sugar production, less on the light. If you take plant phys, plant phys, we do both pretty equally. And so I'm going to give you the big picture idea of the light reactions. And then if you take plant phys, we'll certainly get into more of it. So it's an amazing process. We have this idea where plants are absorbing light energy from the sun, and they're able to turn that into chemical energy, make ATP, which is hugely important because that's how most living organisms have their chemical energy is in the form of ATP. And so ATP is not something that is like stored up in our cells. You make it, you use it. You make it, you use it. And it's just this constant, you make it, you use it. It's not like we have a storage of it. We have other forms of chemicals that we store, like glycogen and things like that. And so it's the same with plants. They have to constantly make ATP, and they have the ability to just soak up the sun and do that. I wish we could do that, but we can't. And so now we're zooming in to the chloroplast for this, and we're going to see how it's the internal membrane inside the chloroplast. Do you remember the name given for the internal membrane? It starts with a TH. Thylakoid. Very good. Thylakoid. So the thylakoid membrane is that internal membrane that's floating around inside the chloroplast, and that's where all the chlorophyll pigment is embedded. And so the light energy will reach the chlorophyll, and the chlorophyll will absorb certain qualities of the light. And so we do have to factor in, you typically get shown this biochemical equation, but don't forget you need to have light and chlorophyll in order for this to actually work. And so this is the typical chemical reaction that they use to summarize both parts of photosynthesis. So this is taking in the light reactions and the biochemical reactions that are used in sugar. You see CO2 there, water, light, chlorophyll pigment, and then you get products, C6H12O6, and then oxygen gets given off, and water. So for this class, I don't really focus on oxygen being given off. Yes, plants are doing that, and we have much to be grateful for because we wouldn't exist, right, without the oxygen. So absolutely, it's super important. However, for photosynthesis, that's not really what we should be focusing on if we're thinking about why is the plant doing it. It's not really to give us oxygen, all right? So we're going to kind of put oxygen on the back burner and not really think too much about it. So if I say to you, C6H12O6, what kind of sugar do you think about? Glucose. Absolutely. That's what I think about when I hear someone say C6H12O6. It kind of gets drummed into your head through a variety of different classes and information that that's glucose. But that's not really the sugar that gets made through photosynthesis. That's not the first sugar. And so it's a real misconception, which I totally get, because before I learned more about photosynthesis, C6H12O6 is glucose. That's what you initially think of. So hold that thought. But glucose really isn't the first sugar that gets made. It's actually sucrose. That's what the plant cares about. Sucrose. So its goal is to do photosynthesis, take in that CO2, and make sucrose, not glucose. And it's sucrose that the plant will use to send through its whole body to go nourish other parts of its body that can't do photosynthesis or that can't do enough photosynthesis. So we'll talk about that as well. So this is a pretty involved process. I'll show you what I mean in a minute here with some visual slides, but let's look at the big picture idea in a visual. So this is the big picture idea again of both parts of photosynthesis. So they've cracked open a chloroplast and you're looking inside of it, and they're showing the thylakoid, or at least the stacked region of a thylakoid. Do you remember what a stacked region of the thylakoid is called? It starts with a G. Yeah, wow, grana, yeah. And so that stacked region they're showing, the grana, granum, singular, I guess. But what you see there is light striking. So they colored it green to show you that that granum has a lot of chlorophyll. Light energy is striking that. The chlorophyll is absorbing that. And then you see down here in the lower left of the image, water. Water is going through a reaction, and you see oxygen is one of the products. So what they're trying to imply there is that water is getting, I tend to say, stripped of electrons. Electrons are getting grabbed off of it and getting sent into an electron transport chain process. And if you take electrons off of water enough times, you're left with oxygen. So that's why plants are able to give oxygen off. It's really because they're using water as a source of electrons. Okay. Now, not all organisms that do photosynthesis will do that. So in my other class, I'm going to be talking to them soon about how bacteria actually don't use water to strip electrons out. They use something else. And so they won't give off oxygen. They'll give off other things, right? But this is usually when people start talking about photosynthesis, this is what they teach you. And true, it's a very, very common with plants. All right, so those electrons coming off of water, they'll enter into an electron transfer chain. I'll show you that in a minute here. And what you see also here is this NADP plus and ADP entering into the system. And then you see by the time it's all done, they're trying to show the finished products up here are ATP and NADPH. Okay, so by the time the electron transport chain, the light reactions are done, you will have ATP and you will have NADPH, which is wonderful for the plant. And then you see those two products are moving into another reaction pathway, which is called, whoops. Which is called the Calvin cycle. And that's the cycle we think about when we start thinking about part 2 of photosynthesis, where they take in CO2 and make sugars off of that. So that's what you're seeing there. And then you see the sugars down here. So remember, that's really sucrose, what they care about. It's not glucose. All right. So here's another image of the two phases of photosynthesis. So on the left, you have the light reactions. And then on the right are what they call the carbon reactions. Some people call them carbon fixation reactions. When they say fixation, what they mean is you're fixing CO2 into a sugar. That's what they're implying. Some textbooks or sources might say light dependent. And I think your textbook, it does say this, light independent. No, that's a big no-no. That should have been corrected in one of it's on its 15th edition. It should have been corrected by now. Please don't refer to the carbon reactions as light independent, because as you'll learn if you take plant phys, I'll tell you right now, there's several enzymes in the Calvin cycle that have to have light to function. So they're not light independent. Okay, and they don't happen at night. So the Calvin cycle is not something that really cooks along at night for most plants. Okay. But okay, so you see the photosystem 2, photosystem 1, you also see written here. So I'll show you what that means. So this is a slightly different depiction of what I just showed you. So whichever works. And that equation that I have up in blue there on the top, that's how I really want you to think about photosynthesis, okay? So they simplified it compared to the one you just saw in the previous slide. CO2, water, light, and chlorophyll, and you get this CH2O with parentheses. So CH2O, you put a italicized substance. When you write it that way, that's the basic building block, in this case, for carbohydrate, CH2O. And so it's a more, it doesn't make you think about glucose, right? And so CH2O plus oxygen are the products. Some people call the Calvin cycle, Calvin cycle, C3 cycle, that's all the same thing, the Calvin cycle. They also might call it photosynthetic carbon reduction cycle, which the acronym for that is PCR. When I say PCR to you, you think about this phrase? No. So I never use this one because polymerase chain reaction has kind of usurped that acronym so totally that if I say PCR, I'm just going to confuse all of us, I think. So no. So, but I tend to say Calvin cycle. It's named after Dr. Kelvin. But sometimes on exams, I might write it as C3 cycle just because it's shorter and doesn't take up as much space. Okay. Okay. So let's zoom in on the light reaction and hit the major points. So we're zooming into the thylakoid, and this is where we're going to see water is getting split apart, which means they're stripping electrons off of water. And then oxygen will get released, which we don't really care about for this discussion. And then protons are also getting released. Okay, so if you look at what happens when they strip electrons off of water, electrons will get sent into an electron transport chain process, but the other products will be protons, H+, protons, and oxygen. So the protons are going to be really important. Oxygen, let's just leave that on the back burner. And so they're going to strip electrons off of water and send them into an electron transport chain process, which is long and complicated and has lots of players in the game. Basically, it's just this hot potato game of passing electrons from donor to acceptor on down the line until you finally get to the end. And then something magical happens. So as all of this is happening, we're going to see it creates the conditions that allows for ATP to get synthesized. And you need that. You need that ATP in order to do the Calvin cycle. The other thing that happens during the electron transport chain process is the very end electron acceptor is called NADP+. You have to be precise. NADP+ is the electron acceptor, the terminal or end electron acceptor. And when it accepts electrons, we say that it gets reduced to NADPH. Anytime a molecule accepts an electron, it's getting reduced. And so it's getting reduced to NADPH. That is also being used for the Calvin cycle. So by the time the light reactions are done, you've created a situation where ATP can get made. That's awesome. NADPH is formed. And then those can immediately start participating in the Calvin cycle, which is also happening in the chloroplast. Okay, it's all happening in the chloroplast. Okay. So I'll show you an image that I use in my plant phys class all the time as kind of a template for talking about the light reaction. So what we're trying to show here is the internal membrane. So that membrane that you're looking at is the thylakoid. Okay, that's the thylakoid membrane. And then you see that there's these complexes that are embedded in the membrane. So there's one that's called photosystem 2, and there's another one that's called photosystem 1. And you can see how those are big, and they span the entire width of the membrane. So we say they're transmembrane complexes. Trans just means along the whole width, in this case, of the membrane. So they're big. So they don't move around in the membrane. They stay put. Then you see this other one called cytochrome B6F. That's another big one. It's transmembrane. And then you see the ATP synthase. Again, huge. Spans the entire width. So we have 4 transmembrane complexes that we need to think about. And like I said, they're so big, they just kind of stay put. Once they get made and put into the membrane, they're kind of stuck there. But they're part of the electron transport chain process. So you have to have a way for electrons to get to these different complexes. But if they're too big to move, well, then you provide smaller molecules. And so you are getting a hint of that here with this PQ to PQH2. These are what we call mobile electron carriers. Okay, they're small. They like to grab electrons and pass them on, right? And they can move. They can move within the membrane. So we see a mobile carrier, all right, of PQ, mobile electron carrier. There's one. Do you see maybe another one? What's the initials on another one there? Something small. PC, there's another one. There's another plastocyanin, that's what it stands for. PC, that's another mobile carrier. Any other small things that you see with initials? I see 2 more. FNR and FD. Those are mobile carriers as well. Okay, so those big transmembrane complexes, they do really important stuff, but they can't move. Those mobile carriers are other players of the game where they're very quick and mobile and agile, and they can transfer electrons down the chain. Another thing you see here is that on the lower left of the image, whoops, you're seeing water. And they're trying to show how if you strip electrons off of it, so you see this electron within photosystem 2, that's coming from water. And then you can see that when you do that, eventually you're going to get oxygen, and then you're going to get this proton buildup. So remember, when you look inside the thylakoid membrane, the internal portion of the membrane, like if you were to pierce into it and look inside, it's kind of like your intestines. Oh, if you were to peer inside of your intestines, we call that the lumen. Okay, so that's the inside of the thylakoid membrane, lower part of this image. And then the watery portion that is inside the chloroplast that the thylakoid is floating around in, that's called the stroma. Okay, so it's important that you think about the orientation here of the chloroplast, thylakoid. So you see that some things are happening in the lumen and other things are happening in the stroma with the membrane separated. And that's really a nice way to set this up. Because what it's going to do is it's going to create a situation where you're going to see protons building up on one side of the membrane. You're going to see lots. If the artist had been a little bit more generous, they would have drawn more protons showing up in the lumen, fewer protons in the stroma. Okay, so this is one of the goals of the light reactions, is to create a proton gradient. Some people call it a proton motive force, which is also accurate. Proton motive force or a proton gradient. Proton gradients are huge. Many, many living organisms play this game of how can I create a proton gradient given my surroundings and what I'm dealing with in my life? How do I get a proton gradient? Because if I can do that, I can create a situation where I cause ADP, organic phosphate, to react, and then I'll get that lovely ATP. Right? So in order to get ATP, they have to play the game and create a situation where they get a proton gradient across a membrane. Here it happens to be the thylakoid. You're doing it right now in your mitochondria, across your membrane in the mitochondria to generate your ATP. Unfortunately, we can't do this. We don't have chloroplasts in our body, but same kind of game. Let's figure out a way to do a proton gradient. And so here you're seeing the protons in the lumen. They show them swooping over to the ATP synthase. So if you run this reaction enough, where you strip electrons off of water over and over and over, and you keep this electron transport chain process going, if you can keep that going, you're going to create a situation where they're showing here protons in the stroma are moving into the lumen. Okay. So as the electron transport chain process is occurring from water, starting there and moving to these players, you'll see that there will be proton movement from the stroma to the lumen. And that's also helping build up a proton gradient. That's really key. All right. So again, it's just kind of this game that has evolved of, I want to create a proton gradient. How can I do this? And so this electron transport process, anytime you see in living organisms an electron transport chain process, look for a proton gradient or some kind of gradient. Sometimes it's a sodium gradient if you get into the wacky world of microbes, but for plants, it's a proton gradient. Okay, so you can't really divorce the two. You have an electron transport chain, you get a proton gradient. Electron transport chain, proton gradient, right? And so really, that electron transport chain process in and of itself is really important because it's going to deliver electrons to NADP+. That's wonderful. Because if you can deliver electrons to NADP+, it gets reduced to NADPH. So just looking at the electron transport chain process, that's great. That's a good payoff. Why? Because NADPH is what we call a reducing agent. So NADPH, NADH, there's several reducing agents that different organisms will use. But basically, when we say, oh, it's a really good reducing agent, what we mean is it's very happy now to, in this case, it's going to go to the Calvin cycle and say, hey, I got some electrons. Let me give some to you. All right. So it's good at donating off electrons in another pathway. And what we care about for this portion of this class is the Calvin cycle. So once NADPH gets made in the stroma, the Calvin cycle happens in the stroma as well. So NADPH gets made, it's going to go right into the Calvin cycle and say, I can give some electrons to keep the Calvin cycle going. So that's huge. That's a great payoff. So in and of itself, the electron transport chain is super important, but it has a dual function. It's allowing for NADPH to get made, but it's also creating a proton gradient. And as those protons, build up, then what happens is those protons, by the laws of diffusion, they want to diffuse back into the stroma, but they're a charged molecule. Can charged molecules go through the hydrophobic region of the membrane or any membrane? No, they can't. So they're forced to go through the ATP synthase. So as they flow through that, it actually allows for these subunits to rotate, create a torque force, and it causes the ATP and the inorganic phosphate to physically react, and then you end up with ATP. So they often refer to the ATP synthase as a little molecular motor, because it actually, the flow of protons creates a torque force, and it allows for ATP and the inorganic phosphates react. It's amazing. And so then you end up with wonderful ATP, which, as we know, we all have to have that to survive. So again, the ATP is right there in the stroma. That's where the Calvin cycle is cooking along. And so ATP can turn around and say, here, I'll help out with the Calvin cycle. So this process is really, really amazing because let me go back. Where's the, because as you have these electrons going, almost starting from water, getting stripped off of water, and then they get passed down the chain. And then this FNR protein is going to participate in that very final reaction where you end up with NADP plus getting an electron and getting reduced to NADPH. And as that's all happening, you get a proton gradient. You get protons building up because of water getting stripped of electrons. That provides protons. You get protons getting shifted from the stroma over to the lumen during the electron transfer chain process. And so that proton gradient then allows for the formation of ATP. Questions on the light reaction? My guess is most of you, unless you've had FIDS, most of you have only had touches of this in maybe BI 111. And maybe you got a little bit of intro in your K through 12 at some point, but probably not a lot. So if this is your first stab at it, really give this some thought. And what I just described to you is just kind of scratching the surface. What's really happening here is way more detailed and phenomenal than what I just described. And I'll get into that in Plant Phys, certainly. But this is a good introduction. Okay. And I really, really, really want you to think about this idea of this electron transport chain linking to a proton gradient, because your other biology classes, if you take any other phys classes, that's going to keep coming up. And so if you can get that kind of global idea, like all living organisms tend to do this game, and there's definite payoffs to this electron transport chain. Okay. Okay, we'll look at this again next lecture. So by the time the light reactions are done, you have NADPH and ATP. So then we can think about the biochemical reactions, which is the Calvin cycle. And that's all happening right in the stroma, the watery portion of the chloroplast. And so the very, very first step of the Calvin cycle is the plants will open their stomata, take in the carbon dioxide, and deliver it to the chloroplast. And it will react with this RUBP molecule, which is a 5-carbon sugar. And I have it written out in the next slide. We're going to see that with the Calvin cycle, at discrete parts of the Calvin cycle, you need to put in ATP into the reaction pathway and NADPH. Okay, but this very first step of CO2 and RUBP reacting, that's all spontaneous. You don't need to push it with any kind of energy or reducing molecules. Okay, so if the plant can open its stomata and get the CO2 in, and if the plant has plenty of RUBP ready to go, these two will just automatically react. And you're going to end up with a product that's going to continue on in the Calvin cycle. So this took quite a bit of effort. So up top, on the very, very top, you're seeing ribulose 1,5 bisphosphate. They only have it down here as biphosphate. It should really be bisphosphate. So I think that's a typo because everywhere else we talk about it as a bisphosphate. Okay. So those gray balls or circles, those are carbon. So 1, 2, 3, 4, 5 carbon sugar. Okay, with 2 phosphates on either end. This took forever to figure out. They knew that CO2 comes in and sugars eventually get made, but they didn't know what it reacted with, and it took forever. They knew that the first stable molecule was PGA down here off to the right, which stands for phosphoglycerate, 3-phosphoglycerate, PGA. So 3, the phosphate, well, I was giving it away. There's 3 carbons. So when they were looking for what does CO2 react with, they were looking for a 2 carbon. Because 2 + 1 = 3, we know that the first stable molecule is PGA, it's 3, so there must be a 2 carbon. And they looked and looked and looked and couldn't figure it out, couldn't find anything. And then Kelvin, his full name is Melvin Kelvin, by the way. Probably got teased a fair bit on the playground, I'm guessing. He came along and said, well, there's more than one way to get to 3. Why don't we go to 6 and divide by 2? I mean, it's more complicated than that, but essentially that's what he allowed. You know, like, let's think a little differently about this. He said, you know, what about a 5 carbon sugar? Maybe CO2 reacts with that. And when they started hunting for that more carefully, now you have to realize this was decades ago when technology wasn't that good. So there were so yeah, by his help, they figured out it was RUBP and CO2 reacting. And the reason this was such a problem is this molecule that immediately gets formed is super short-lived. And the technology back then, they couldn't pick up on it. And so they missed it. And all they kept seeing were these 3 carbon PGA. And so through more careful work and Dr. Kelvin's help, they figured out that first time. And because of that, he won the Nobel Prize. And he actually went to undergraduate school up at Michigan Tech University in Houghton, Michigan. So when I did my doctorate up there, there was a biochemist up there who was very quick to point out that Dr. Kelvin did his undergrad there. So it's kind of all right. So you see in that part of the cycle, there's no ATP, no NADPH. It's just going to happen. Okay. So once you can see there's 2 molecules. That 6 carbon breaks into 2 identical molecules of PGA. All right. But now, if you look at the next phase on the Kelvin cycle, you go from PGA to the next phase. No, the next phase is PGA goes to G3P. That's really the next phase of the cycle. So if you look at that stage of the cycle, now you're starting to see ATP is getting used. And you also see NADPH is getting used. Okay. So that second phase, you do have to have some help to go from PGA to G3P. Then you see this green box on the lower left where they say, after you do 3 turns of this cycle, one of those G3Ps can be siphoned off in order to make sugars. All right, so that's where we start thinking about sucrose getting made. Okay, so those sugars that they're talking about is really the idea of sucrose production. And I'll talk more about that. And then the very last phase of the Kelvin cycle is going from G3P back to RUBP. And again, you can see you need ATP for that. Not NADPH though, just ATP. So you have to keep the Calvin cycle turning round and round and round and round all day long, all day long, all day long, so that the plant can have something for CO2 to react with. You have to have enough RUBP for that CO2 to react with. So you keep this going around and around and around and around, and then every 3 turns, you can siphon some of that G3P off and make sucrose. So the Calvin cycle isn't like, you don't see sucrose in here anywhere in the Calvin cycle, but that G3P, which is part of the Calvin cycle, will get shunted off to another pathway for sucrose. And so it's linked to sucrose synthesis. And you have to have the Calvin cycle going for all of this to work. Okay, we got to stop there. And so we'll do a recap. So give this some thought, probably an eye clicker on Wednesday with the what we've covered today.